All right, thank you, Linda. My name is Shashan Liu. I co-chaired the autonomous machine computing with Professor Kodia from UC Irvine. So today I'm going to talk about this very new application, which I believe it's a huge driver for semiconductor in the next several decades. Next slide, please. So here's what we see for the growth of the robotic market. And this chart is not including autonomous vehicles and some other form of robots. I think this one is only industrial robots. But we do see the huge market potential. For this sector, the projected average compound growth is 22%. So the sector by 2030 would have a market size of $1 trillion. But the core problem that we are facing today is that we don't have a good unified compute platform for all kinds of robots. People just use commercial off-the-shelf chips for these robots, which is not optimized. What we aim to do is to implement a computer system to handle all the basic functions in hardware, such that we can build computer architecture and computer systems for various kinds of autonomous machines. Next slide, please. So an analogy, if you look back into history, Paulo just showed that there are several demand drivers for the semiconductor industry, including personal computing, mobile computing. Mobile computing especially rises in the past about, 10, 20 years back. It's not that long ago. But if we pick up a old Nokia phone, we realize that back then, although it's an essential component to have, but it's fairly small market size, about $10 billion. If you look into the phone, about 90% of the compute power goes to the basic functions, such as phone calls, encoding, decoding. Only 10% of the compute power goes to end applications. But if you look at it today, it's a $800 billion market size. And 90% of the compute power actually goes to end user applications. Only 10% handles the basic functions. So we have seen the evolution of mobile phones. Next slide, please. We believe the same thing would happen in robots. So we have profiled the computing workloads from many different types of robots. What we have found is that today we are really constrained by the compute power within the robot. Pretty much over 90% of compute power goes to basic functions, including robotic perception, robotic localization, planning, control. Only a very small percentage goes to application. That's why the sector has not exploded per se. But if we could design systems that constrain or limit the compute power to the basic functions within, say, 20% of the total compute power, and unlock about 80% of compute power for the end applications, that will become a very interesting factor. And so that has been our goal. Next slide, please. If we zoom in to the workload of various kinds of robots, for example, on this figure, on the left side, you see a level 4 autonomous vehicle. On the right side, you see a very simple form robot, which is a cleaning robot. You see very similar patterns, such that there's a front end that ingests a huge amount of data, sensing data. And then gradually, as it progresses towards the end of the pipeline, the amount of data reduces. From autonomous vehicles to robot cleaners, we see the same pattern. So we are fairly certain what kind of computer architecture we can design for this type of robots. Next slide, please. And then to make things more complicated, these robots do talk to each other. So communication is another essential part for these kind of computing workloads. For example, this is a figure of a infrastructure vehicle, a cooperative autonomous driving system, meaning that you deploy units on the roadside to give data to the vehicles so that the vehicle can see, say, 10 miles out to eliminate blind spots. Also, the roadside can give command to the vehicle such that we can improve the traffic efficiency. The same logic can apply to, for example, cooperative robots as well. So communication is another key domain that we have to optimize for. Otherwise, we cannot optimize the whole robotic ecosystem. Next slide, please. So based on that, very short summary, it's the very beginning of this robotic sector, autonomous machine age. Then we are studying, we are researching and studying heavily in the computer architecture side. We have produced some very good results. But on the technology electronic side, we need a lot of help. That's why we joined the roadmap. For example, there are several key technology that's arising in recent years. For example, SPAT plus micro-LED technology that can be used for sensing. With this kind of technology, we can greatly improve the sensing capability of different kind of robots. For compute, we can have FinFET nanosheet kind of technology to enable faster computing within the robot and lower power consumption as well. And we have technology for 6G front end, such that we can facilitate the communication between robots and autonomous vehicles. And of course, we have eFuse NVM for the storage system. We really have to combine all these different kind of technology to enable the whole autonomous machine age to go forward. So we're looking forward to working with you guys. Since it's an application area, we'll touch upon many of the topics that we will cover today and tomorrow. But I do believe that autonomous machine is a key demand driver for semiconductor for the decades to come. And looking forward to collaboration as well. And thank you very much. If you have any questions, now is the time to for us to communicate.
Thank you, Xiaoshan. Are there any questions?
I just wanted to add a comment. This reminds me on 1996 when we began the i300i that was supposed to do the transformation of the wafer from 200 millimeter to 300 millimeter. And then we were able to introduce automation. And one of the main accomplishments was that several companies had bits and pieces of it, but there were no standardized, so they were very inefficient. And we devised a system that has standardized cassettes and control of all the wafers in a factory. And in the last few years, I visited few factories, and they used to have thousands of people. Now they have 30, 40 people in a room controlling the whole factory. And just as an example, the labor used to be in the mid-90s, 15% of a wafer cost, and nowadays about 2%. So this is a small example, but shows what Xiaoshan was explaining, that standardizing, is a key element in this proliferation robotics. But there are many devices that are missing and they haven't been paid attention to. And so we hope that with the joint effort that we're planning on having with Europe, Japan, and the US, we're going to put these devices into the prototyping category, so that in the next 2 years, these devices will be demonstrated and they will make their way into high volume manufacturing. So I'm very excited about these two new chapters because they address fundamental problems that haven't been paid attention to.
I'll make a comment. This is Scott Holmes, and I've heard some statements about semiconductors. What I'm seeing already here is like with the SPADs and the micro LEDs, it's not just semiconductors, involved there, but it's more. It could be photonics as well, and we need to be talking, I think, in a more general, even electronics. When you get photonics. We're still used to talking about semiconductors when it's broader, I think, now. So,
Scott, you're absolutely right. The RFI that we submitted to both NIST and DoD include precisely what you said. I just talk about semiconductors. I didn't mean to limit that. It's much broader than that. That's why these devices are not paid attention to. So you're absolutely right.
Okay, thank you very much.